A steel plate, the length of a gymnasium, slides into a cutting machine that allows no quarter-inch of error. The first cut on a ship longer than 3 football fields. 55,000 tons of metal folded around a hold, built to swallow 2 million barrels of crude. One voyage carries 10% of everything America burns in a day. China builds one from raw plate to open ocean in under 2 years. The United States cannot build one at all. And the ocean these ships cross does not care who made them. It tries to destroy every one, every day, for decades. Stretch a VLCC out, and it runs 330 meters, bow to stern. 3 football fields laid end to end still fall short. The deck alone spans 60 meters wide. Lay a 6-story apartment building on its side across the beam, and it fits with room to spare. But dimensions only tell you what the ship looks like standing still. The moment it moves, physics turns the entire structure into a problem that never stops trying to solve itself in the worst possible way. 2 million barrels of crude oil sit inside that hull. Crude does not rest. Every wave sends it surging forward, slamming against bulkheads, rebounding sideways, crashing back. The liquid hunts for weak points, the way water finds cracks in a basement wall, relentlessly, patiently, around the clock. Engineers call this free surface effect, and it does not just push against the steel. It shifts the ship's center of gravity mid-ocean, mid-storm, mid-everything. A vessel that was stable 5 seconds ago can start rolling unpredictably because the cargo inside decided to move. And the ocean attacks from the outside at the same time. North Atlantic swells routinely reach 15 meters, walls of water heavy enough to bend structural steel on contact. Pacific typhoons have swallowed entire vessels without leaving wreckage. Saltwater chews through protective coatings and goes to work on bare metal underneath, grinding away at welds, joints, and seams year after year. Corrosion does not announce itself. It eats quietly, invisibly, until a structural survey finds what it left behind. The hull absorbs all of this: the internal battering, the external assault, the relentless chemical erosion, not for a season, not for a crossing, but every single day for 25 to 30 years, thousands of voyages, millions of nautical miles, an existence defined by forces that never take a day off, trying to pull the ship apart from both directions at once. And somehow, one country can take raw steel plates and turn them into this in under 2 years, a process that begins with a single cut, allowed less than a quarter-inch of error. That quarter-inch is where everything lives or dies. Every one of those 55,000 tons of steel plate feeds into computer-controlled cutting machines that allow no deviation beyond that margin. The strictness is not perfectionism. It is survival arithmetic. A quarter-inch error on one plate travels forward through every step that follows. It becomes a centimeter off on an assembly. The centimeter becomes a gap in a joint. The gap becomes a structural weakness, hiding inside a hull that will spend 3 decades getting beaten by the ocean from both sides. Errors in shipbuilding do not shrink. They compound silently until something cracks that was never supposed to crack. The old method built ships the way you build a house, bottom up, one layer stacked on the last, each step waiting for the one before it to finish. That process took 4 to 5 years and left every mistake buried under the next layer of steel. Chinese engineers dismantled that entire approach. They take the full blueprint and slice it into more than 100 separate sections, each one weighing between 300 and 600 tons. Every section gets built independently, pipes threaded, wiring run, protective coatings applied, before it ever touches the main structure. Then cranes that could lift a loaded passenger jet pick each finished block and lock it into position against the others. 100 giant pieces, built in parallel, assembled into a single hull. A ship that used to take half a decade now reaches the water in under 2 years. but speed creates its own predator. How do you take 100 steel blocks, each the weight of a commercial aircraft, and guarantee they meet each other to within the width of a human hair? Because if they do not, every compounding error from the cutting floor arrives at once. Millions of sensors embedded across the biggest Chinese yards feed data through high-speed networks into AI systems that track every measurement, every position, every shift in real time. A deviation the size of a hair triggers an immediate flag, not when a worker notices, not at the next inspection, instantly. A few millimeters off on section 5 becomes a few centimeters by section 50, and a fatal flaw by section 100. The system kills the error before it can travel. Then the welding seals it all permanently. Robotic laser arms work through steel plates 50 millimeters thick, holding identical temperature, identical speed, identical pressure for days without variation. A human welder, no matter how skilled, drifts. Muscles fatigue, attention shifts, and across thousands of hours, small inconsistencies accumulate that no amount of discipline fully eliminates. The robots do not drift. Every joint they seal has to survive salt water, shifting cargo, and ocean storms for 30 years, and the weld that holds on day 1 has to hold exactly the same on day 10,000. That process produces a hull strong enough to cross the most violent oceans on Earth for 3 decades. But a hull without an engine is a steel island, and what it takes to push 300,000 tons through open water is its own kind of impossible. The engine stands 4 stories tall. Its cylinders are wide enough for a full-grown engineer to walk inside during maintenance, and when it fires, it generates close to 100,000 horsepower. But horsepower is not what moves a 300,000-ton ship. Speed is useless here. What matters is torque. Slow, crushing, continuous rotational force that travels down a single steel shaft and refuses to stop pushing no matter what the ocean throws back. That shaft drives a propeller weighing over 100 tons, cast from a single piece of corrosion-resistant metal. One piece, deliberately. Joints and seams are failure points, and failure points invite the ocean in. A propeller built from segments would develop micro cracks at every connection over years of stress, and salt water would find each one. A single casting eliminates the invitation entirely. The blade geometry comes from the same computational fluid dynamics used to shape aircraft wings, because at this scale, small inefficiencies devour money. A 1% improvement in propeller efficiency saves up to $1.5 million in fuel per year on a single ship. Across a fleet of hundreds sailing for 3 decades, that single percentage point reshapes entire balance sheets. But the engine carries a hidden threat that no amount of horsepower or casting precision can outrun. At full power, the engine vibrates at a specific frequency. 2 million barrels of oil shifting inside the hull vibrate at another. Most of the time, those frequencies ignore each other. But when they align, when the engine's rhythm and the cargo's rhythm lock into sync, resonance builds. The same physics that lets the right musical note shatter a wine glass goes to work on welded steel. It does not shatter it. It fatigues it, quietly, cracking welds and aging joints over months and years, stealing operational life the ship was designed to have. The engine never bolts directly to the hull. It sits on a damping system that scatters those frequencies before resonance can take hold, the last invisible layer protecting everything the hull, the welds, and the robots built. Everything described so far represents the tanker China spent a decade perfecting. What it is building now looks nothing like it. 40-meter rigid sails rise off the deck of the Shin Aden, carbon fiber structures tall as a 13-story building, standing on a ship the length of 3 football fields. They are not decorations. They are aerodynamic engines that capture wind and feed it directly into propulsion, cutting fuel consumption by 9.8% under real-world conditions. That number sounds modest until daily fuel burn turns it into math that compounds ruthlessly across decades. On a vessel that devours fuel by the ton every single hour it moves, 9.8% saves millions of dollars per year. Multiply by 30 years of operational life, and a single design choice on the deck quietly reshapes the economics of an entire fleet. The UN Ray Young attacks from a different direction entirely. Stretching 333 meters long and 60 meters wide, it runs a dual-fuel system that switches between conventional diesel and liquefied natural gas depending on which region it crosses and which emissions rules wait in port. Carbon dioxide output drops 20%. Sulfur emissions fall 85%. Those numbers meet the strictest environmental standards in global shipping today, standards most of the existing fleet cannot come close to touching. Every tightening regulation turns older vessels into liabilities and makes these new ships more valuable simply by existing. Then the lifespan. The newest generation of Chinese tankers is engineered to last 30 years instead of 25. 5 extra years sounds small until you load those years with millions of barrels per voyage, hundreds of millions of dollars in additional value sitting inside a hull that burns less fuel, meets stricter rules, and outlasts anything the competition offers at the same price. When every financial incentive, cost, efficiency, compliance, longevity points toward one country's shipyards, orders do not just accumulate. They build a dependency that reaches far beyond the ships themselves. A Greek shipping executive signs the contract for a new VLCC. The price is competitive. The financing comes from a Chinese state-owned bank that spreads hundreds of millions of dollars over terms flexible enough to make the upfront cost nearly vanish, and the ship itself outperforms everything else on the market. The decision feels obvious. What the contract does not spell out is what follows delivery. The moment the tanker reaches its new owner, it carries Chinese-designed systems inside every critical function. The spare parts that keep it running are manufactured for those specific systems. The engineers who understand how the ship was built work in Chinese yards. The software that monitors performance, the maintenance schedules, the technical upgrades that extend operational life, all of it routes back to the same country that cut the first steel plate. One purchase creates a relationship that lasts 30 years, and every year deepens the dependency, because switching systems midlife on a working tanker is not a realistic option. It is a rebuild. The financing turns that dependency into a pattern. Chinese banks did not just offer loans, they removed the single largest barrier to ordering new ships. Companies from Norway, Greece, the Middle East, and across Asia started placing larger orders more frequently because the financial math bent in their favor in ways no other shipbuilding nation could match. Each order added another vessel to the Chinese ecosystem. Each vessel added another 30-year thread connecting that company's operations to Chinese shipyards, Chinese parts suppliers, Chinese technical support. Step back far enough, and the picture stops being about ships. About 60% of all oil traded on Earth moves by sea. The vast majority of those vessels came from Chinese yards. China does not own a single oil well. It does not set production quotas. It does not need to. It built the vessels that carry the oil, finances the companies that operate them, and supplies the parts that keep them running for 3 decades. The ships being ordered and welded together right now will still be crossing oceans in 2055, which raises a question that does not come with a comfortable answer. The ocean does not look the way it used to. Not as a boundary between nations, not as empty space that ships happen to cross. It looks like infrastructure, a network somebody built, somebody maintains, and somebody increasingly decides who gets to use. From raw steel plates, to robotic welding arms, to carbon fiber sails, to financing terms that make it easier to say yes than to walk away. One country shaped the system that moves energy across this planet for the next 3 decades. The next video pulls on this thread in a direction most people have not considered, because the country that builds the ships also builds something else entirely.